Okay. Hi, my name is Gabrielle. I'm doing part C, so I'm going to derive a differential balance equation for a concentration and temperature for the exothermic CSR-TR. So this means that it is a constant stirring tank and there is a cooling jacket. So first, let me just draw what is happening. So we have our tank. Our tank is being stirred. This is being stirred, and we're having a Q in. We have a Q in, and we have some Q that's leaving, or concentration that's in this. So the concentration, there's a different concentration in. So QA in, and then we have QA, and it's inside. So we know this is a well stirred. That means that the concentration that's leaving the system is the same that's inside the system, since it's well stirred. So it should be QA, right? So now that we know this, we know a couple key factors that this has a cooling jacket. When it has this cooling jacket inside, there's a temperature, the temperature that's being cooled, and then there is the temperature that's. So let's look at some of the initials that we know. We also know we have a K initial. So K initial or K naught. We know our equation is K naught times EXV of negative E RT. So this is going to be helpful when we're solving for K. But this should be it for now. So that we need to know. To begin with, we'll use the initial values for our code. So what we're going to do is we need to know the concentration that's into the system. So the concentration that's into the system is differential of Ca times our volume divided by differential change. So what's coming in and what's coming out? So what's coming in is our concentration coming in is going at a flow rate of Q. And then what's leaving the system is going to be a QA, right? Because it's well stirred, and then it's leaving the same amount of flow rate that's coming in. So QA. And we also know this is the exothermic reaction, and the reaction is eating up our concentration. So we're going to subtract by K, and then we're going to do our Ca, and we're going to multiply. So this is going to give us pretty much, we're going to have to multiply by volume so that the moles cancel out and we'll have joules over. So we have this, we know our V is a constant, so our V is a constant, so it's going to be dCA over dt, and it's going to be, we'll pull out a Q because our Q, the flow rate is going to be equal leaving in and out, so it's going to be Q, and then our volume is going to be C. It's going to be our CAN minus our CA, and then our V's cancel out, so it's going to be okay. So this is going to be the differential change for our concentration. So now we need to find the differential change of our temperature that's inside of our tank. So we know this is going to be temperature. Temperature is in Kelvin, and we want to multiply this by our heat capacity, so CP. So CP is joules over moles per Kelvin. So our Kelvin, grams actually. This is grams. So grams. So that cancels out. So if we want to know that, then we need to multiply it by rho. So, well, we have volume. Let's do rho actually. So rho. So rho is going to be 1 G. This is G over L. And we want to get L out, so we multiply it by our volume, which is just L. So then we have our cancellations. So then we will only have joules. And then we'll do the differential of this, and we'll do it based off of time. So it'll be joules per minute, pretty much. Okay. And so this is going to equal. So what is this going to equal? So we know that our H, so we know that enthalpy pretty much equals our CP over our temperature initial minus our temperature plus COH. So we know that this is going to be our CP, so the first thing of trying to find our energy is going to be our CP. So our specific heat times our temperature initial minus the temperature. And then we're going to add. So what we're going to add is so what we're going to add is that this is a chemical reaction. So we know this is a chemical reaction. This is exothermic. So that means temperature is going to be added to the system. Temperature is going to be released. So we have our theta of our H reaction. And then we are going to multiply this by K. And we're going to have Ca, and then we'll have volume. And then we're going to subtract this by. So we know previously we derived that we have, it's going to be UA. So UA is the heat transfer coefficient of the system times the temperature minus the temperature of the tank minus the temperature of the coolant. So we're going to put that into here, and it's going to be UA times temperature minus temperature. Okay, so I'm going to erase this. So we know that the volume, rho, and our specific heat are all constants, and what we're trying to find is the differential change of temperature, so we can divide everything by it. So we'll have differential change of temperature over the differential change of time is going to equal our oh, and I forgot about the CP. CP to keep our units for joules per minute, I need to have Q. So let me erase. So it's going to be Q, and then it's going to be H. And then after H is going to be reaction K, Ca. So then when we do this, we'll get a CP, and we will have volume left. So we'll have Q over volume of T, 1 minus T plus. So our next one is going to have our CP. It's going to have our volume. So this should have volume. So the temperature, we're trying to find the change in temperature in the tank. Okay, so we're trying to find the temperature change of our cooling of our system. So the first thing that we're going to have is our temperature. The next thing we're going to have is our CP. And then after our CP, to keep our units, we're going to have our volume. And then to cancel out our liters, we're gonna add rho. So then that cancels out grams in CP, and then it cancels out our liters in volume. So then this is a differential. This is gonna be over dt. So the first thing that we wanna do is, we know that enthalpy equals our CP of temperature, initial minus temperature, plus OH, but we don't need that right now. So we need CP over temperature, initial minus temperature. And we know that CP has grams in the denominator, so we're gonna have to multiply this by rho, and we're gonna have to multiply this by well, we need to keep this in joules per minute, so we're also gonna have to multiply this by the flow rate, which is Q. So then we're gonna add, so after we've done this, we know we have a reaction. This is an exothermic reaction, so that means that heat is released, so that means there's gonna be a temperature increase. So we have to add heat to the system, so plus our delta HR, so our heat reaction, times our K times our Ca, and then we're going to need to add, we're going to need to add, multiply this by our volume to keep our temperatures. And then we're going to divide it, and then we're going to subtract, because we have a cooling jacket, so we're going to subtract the energy heat released by it. So the heat transfer of it is going to be our QA minus T minus our temperature of our coolant. So it's Cu times the temperature inside the jacket, no, inside the tank minus the temperature inside the jacket, which is cool. So now we know that we have a differential. We know our rho, we know our volume, we know our CP are being constant. The only thing that's changing due to time is our temperature. So we can move this to the other side and cancel some things out. So we have dt, so the differential change in temperature due to time is going to equal, so rho is going to cancel out on this one, and CP. So the only thing we're going to have is going to be Q divided by V over T1 minus T. And then we're going to have delta HR, and then we'll have our V cancel out. So then it's just going to be a rho over CP. Rho over CP. And then lastly, our UA is going to have nothing cancel out. So T minus TC. And then this is going to be rho, E, and C. Okay, so now this is going to be the differential equation for temperature. And then we have a differential change temperature, differential equation for our concentration. So thank you. Okay, so I'm doing part C and I'm doing part C2. So it says using solve the numerical initial value problem, we're going to use solve IDP, and then we're going to plot the temperature of coolant at 290, and then we're going to do it at 305. So the first thing that we want to do is let's import NumPy as MP, and then the next thing that is from SciPy integrate. We're going to import our solve IDP because we made two differential equation problems, and then we need to solve using that. So also we have to plot out the differential change in our concentration and then in our temperature. So we need to import our subplots. Okay. Okay, so the first thing that we want to do is we're going to put our initials. You can see on this for the example on table 2.3, it gives us them. So we have our Q, which is our flow rate. It's going to be 100. Then we have our initial concentration. It's going to be 1. And then we have our temperature. Initial is going to be 350. 350. Our volume is going to be 100. Our rho is going to equal 1,000. And our CP, our specific heat, is going to be 239. Our negative RH is going to equal 5 e to the 4th. And then our ER was going to be 8,750. And then our K naught is going to be 7.2 e to the 10th. And then we have our UA. It's going to be 5 e to the 4th. And then we have our temperature of the coolant, which, let's do that actually last. So then we have our temperature. So then we have our concentration naught is going to be 0.5. And then we have our temperature naught, which is going to be 350. Okay, so the first thing that we want to do is, we know at our problem it says we want the temperature coolant to start. We're going to start it off at 290, so temperature at the coolant, and that's going to be 290. We also know that this is, we are doing a time variable, so we need to know when our time is going to end. So let's just set this to begin with as 1,000. We're going to change it, but let's just start with 1,000. So the next thing that we want to do is we need to define our equation. So let's just define it as right-hand side. Yeah. And we are going to have this based off of time, and then we're going to have a vector. So the vector, let's unpack this vector. So it's going to be concentration and then temperature, right? These are the two differential that we found. So our differential is going to equal our vector. So the next thing that we want to do is the two differential equations that we derived, our concentration and our temperature. We're going to do those. So on the board, let's do our differential dt. And so the first thing is our Q is going to be multiplied by our CI, so our concentration initial, minus our CA. And then this is going to be divided by V. And then this is going to be minus. Actually, we can make this a little easier. We forgot to initialize. We forgot to figure out K. So let's do KCA because in both equations, K is multiplied by CA. So we can do KCA, so we'll do CA. We're going to multiply it by the equation to find K. So we know it's K rho, K naught times numpy XP, and then it's going to be negative ER times divided by temperature. So this is our equation for that. So now let's come back here and let's just do KCA. Okay. So the next thing that we want to do is after we find our concentration differential equation, let's do our temperature. So dt. So it's going to be Q, and we're going to multiply this by our temperature initial minus our temperature. And then this is going to be divided by V. And then we're going to add, so this is going to be our negative HR times our CK, and then we're going to divide this by rho times our specific heat, and then we're going to subtract this by
So UA times our temperature minus the temperature of the coolant. And then we're going to do divide by, so we're going to do rho times our CP times our volume. Okay, so now let's return this. So we had our vector starting as concentration and then temperature, so we have to do the same thing with our differential. So we have to do the differential of concentration, then the differential temperature. So it's going to be dc dt and then dt dt. Okay. Okay, shift enter. Okay, so after we have this, now we can use our solve IDP equation because we have our two differential equations. So we're going to do solve IDP. So the first thing that we want to do is put what is our differential that we defined. It's going to be RS. And then we have to do our initials of our time. So it's going to be T, and then it's going to be and then we have to do our initials for concentration and our temperature, which we already have. So then it's going to be, we have to do C. We have to do our concentration first, and then we have to do our temperature because it's in the same format. And then let's do our method as equaling our Radu method. And then we have our just our dense output. We need this to equal true so that we can choose which times we want to plot this for. So let's see if this works. So on the solve, let's give this a solve integrate. So that means this is good. So let's just make this equal resolution, give this a variable. Okay. So the next thing that we want to do is this needs to be on, we need to make our x-axis, which is going to be our t-plot. So our time. So our t-plot is going to be MP line space. And it's going to be from 0 to the time that we specified it's going to be ending, and let's have 1,000 points. Okay, so after we had our after we initialized our x-axis, now we can solve for it. So resolution and then solve, and then we can just put our t-plot in here. Okay, so what this is going to give us, this is going to give us two arrays, and then they're going to be in our CA, our concentration, and then our temperature. So we can just equal that. And so let's see. Okay, so the next thing that we want to do is after we have this, let's make our subplots. So figure equals make underscore subplots. Okay, and so since we're going to have two graphs, we want to have rows. We're going to have two rows. We are going to have one row, and then we're going to have two columns. Okay, so then we're going to have fig dot at scatter. So the scatter plot that we want first, our x-axis is our time plot, and then our y is going to be, this first one is going to be our concentration. Let's put our name, and let's put concentration. I don't know why I didn't do that. Okay, and then we want this to have a mode. We want this to be line. And then lastly, our row, this is going to be in row 1, and this is going to be in column. So let's just copy and paste this over. And let's do this for our temperature. So temperature, so put temp. And then this is going to be in column 2. And so then let's just update our layout. So fig dot update score layout. This is going to be height equals 600. Width is going to equal 800. Okay, so let's do shift vector. Let's see what we're working with. Okay, so this is pretty much saying that as our concentration is shooting up, so we're starting at a really small concentration, and this is going to make our temperature drop really low. But as our temperature drops, our concentration is going to go up. So our next thing that says is that we want to look at 305. So let's look at 305. And also while we're here, let's change our time to 10 minutes instead. Shift enter, shift enter, shift enter, shift enter, shift enter. Okay, so this is a little interesting. So you can see that it's kind of oscillating. So we're doing the opposite of both sides. So the concentration is starting at a 0.5 and it's gradually going down. It's going really sharp down. So let's look at the temperature. So we're starting at a 350, right? And we're going to shoot up. So what's happening is the temperature of the chemical reaction is going to eat up our concentration. So when it's eating it up, it's going to decrease. But also this is an exothermic reaction. So as our concentration is decreasing, our reaction is eating up our concentration, and that's going to make our temperature shoot up. So now we're at a really low concentration and we're a really high temperature. And so what's happening is we're putting more concentration into the system, but there's not enough to have a really good chemical reaction. So we're going to go back down with our temperature. And as we're gradually going up with our concentration is going to be at its peak. And then our temperature right here is going to shoot up again. So as it's shooting up again, our concentration is going to go down again. And then it's going to just oscillate. So when the temperature goes at its peak, when the temperature goes at its peak, the concentration is low. When the concentration is at its peak, the temperature is low. And then it just goes back and forth and back and forth. So that is why it's oscillating. And that is it for this question. Thank you.